So, hello and welcome to this short webcast session on the subject of 5G and R in the context of industrial applications. My name is Mike Hottkamp. I'm working in the technology management group of ROHDE SCHWARZ, dealing with test and measurement solutions for 5G primarily. So the session is structured in maybe two main parts. So the first one will be the explanation of the key characteristics that we have in 5G and R to support these specific use cases out of the industrial environment. And on the second part, I'm touching more the real implementation of these networks and also what the test and measurement challenges and solutions are in this case. So let's start then. As an introduction, we shortly look into the already history and in the current developments in 5G and R. So, commercial deployments are existing already for quite a while, since the year we are in commercial operation, whereas the initial commercial deployments are focusing on enhanced mobile broadband services. So the first wave on enhancements that we see in the standardization environment, they arrived at 3P release 16, and they are mainly driven by two important vertical markets. These two important vertical markets are represented by two fora: the 5G ACAA, so the Association for Connected Industries and Automation, as well as the 5G AA, the Automotive Association. Both groups have influenced the technology with requirements that formulate specific requirements towards the technology for their use cases. This release 16 is now supposed to be finalized in September 2020, but we can already see that some of the improvements are formulated in how they will look like. Obviously, this specific use case that is also denoted as ultra reliable low latency communication spans up a new triangle. And in these use cases, we usually discuss security, reliability, and latency aspects as they are most important here. Throughout my presentation, I will not touch security because it's on its own such a big topic that it will not fit in 35 minutes. I will very much discuss reliability and latency later on. But even with Release 16, of course, this is not the end of the 5G and R evolution. Release 17 is already in preparation and started. It's anticipated to be finalized in December 2021. The subjects you can see already today are non-terrestrial networks, so things that are maybe up in the air. There's a discussion of new frequencies even above the existing ones in FR2. And there's also a subject in our light, which is dealing with the massive number of connections to be supported. So all in all, we can say 5G is clearly not a 100-meter sprint. It is going to be a marathon, and it will work and exist for many years to come. And we will see many more enhancements in the future. But let's come to the 5G and R technology for our specific use case, industrial applications. So what are the inherent supporting technology components that make 5G and R so suitable for this use case? I will discuss first the latency improvements or latency aspects that are available with Release 15 already, so with the basic system. One subject is clearly the flexible numerology that is supported. Because of that flexible numerologies, we have different subcarrier spacings. And with the high subcarrier spacings, we support small or short symbol durations. And even only a few number of these symbols can be combined into a so-called mini-slot operation. That may go down to even 2 symbols only. So obviously a mechanism to support low latency communication. Also, we are operating a TDD system, and that is again very flexible to be configured. You can see here the downlink and uplink slots that are maybe allocated, and there is also the possibility for flexible slots. And for these flexible slots, also the number of downlink and number of uplink symbols are very flexible. In that sense, you can choose from a variety of configuration possibilities to support best your own application. If that is a low latency application, then you choose obviously the right slot format for this. Another aspect is a very flexible HARC system that is available with 5GNR. So on the left-hand side picture here, you can see the basic mechanism that you are used from existing, or you're used to also from existing technologies. Usually the base station is giving the UE a certain grant, and then it can send data in uplink, or vice versa. The base station is sending downlink data, and after reception, then the uplink or the acknowledgement of that correctly received data packet is acknowledged in uplink direction by the end user device. Now these times K0, K1, K2 were in past technologies usually very much fixed and at a certain size. Now in 5GNR these can be configured very flexibly, and they can even go down to 0 slot. That means in terms of symbols. So for our application here, industrials, Industry 4.0 applications, it would be possible to have the downlink packet received and within the same slot to send the acknowledgement in uplink direction towards the network. Again, something for low latency achievements in the communication link. There's also grant-free uplink transmission. So in addition to the already known semi-persistent scaling mechanism SPS type 2, where the base station is allocating periodic resources that can be activated via the DCI formats, there is a new mechanism, and that is called SPS, semi-persistent scaling type 1. In this case, you can configure a fixed reservation of shared resources for the end user devices, and they may use them at any time if they have data to transmit. So it's overcoming the bottleneck of a certain initial time until you are able to send your first data in uplink direction. Next one is maybe touching both latency and reliability aspects, because obviously the mobile edge computing possibilities allows you to improve both the latency as well as the reliability in the system by simply placing the application servers as close as possible to your machines in an industry hall, for instance, you like to connect. That is obviously a mechanism that is very suitable for industrial applications. And there's also an important one for specific reliability and latency aspects here, because the 5GNR technology allows you to identify the traffic flows and mark them with certain quality of service flows. And with this marking and categorization, you can have dedicated quality of service profiles for industry applications, and they have delay critical constant bitrate profiles, or these are constant bitrate profiles with delay batches defined in the range from 5 to 30 milliseconds. So with this marking on the traffic flows, you allocate also on the radio access network specific data radio bearers with those characteristics that ensure that this delay and this delay budget as well as the data rate is achieved according to your needs. Finally, on reliability aspects only, so the remaining slides are discussing reliability. We have, first of all, in release 15 already added new modulation encoding schemes that allow for very robust transmission, first of all, and also they target a very much higher block error rate than it used to be in the past. So this block error rate target is here 10 to the minus 5. It used to be only 10% block error rate in the past in the existing tables. So you see that comes at a price, because the spectral efficiency obviously is very low in these modulation coding scheme indexes that achieve a very reliable transmission. Also, there is an addition, sorry, in terms of the hardware repetition process. So usually you send your data packet in downlink, you, if not received correctly, request a retransmission and so on until it is received correctly, and then you send your ACK. Now, an improvement has been included in specifications for 5G NR that allow you to send from the beginning certain data packets and repetitions in different formats. And obviously, if you do that right away, that will increase the likelihood that you receive that packet correctly, and also by this ensure a good, reliable communication. The final slide for reliability then, there's a basic mechanism that allows you to do packet duplication on PDCP layer. So within a PDU session then you've got the same packet that is sent twice. This can be used in a carrier aggregation, pure carrier aggregation fashion, where then the packet data packets are sent on different carriers. You can also use that in combination with the so-called feature dual connectivity, where then also both packets or the same packet is sent twice. All the details are described in specifications 38.3.23, as you can see here. And the final subject here is the well-known mechanism for coordinate multi-point transmission comp. If you use different access points and they send this data from different direction to the user equipment of interest, obviously the different propagation channels will allow you to ensure or to increase the likelihood for good transmission, because they're just different and you can sum up the different signal entry via these different paths. So these are all the mechanisms you've got already in 3GPP release 15. But I mentioned earlier that in release 16 there have been a lot of improvements because of the influence of the 5G ACIA, as an example. What is now the main improvement here? Well, the main requirement was, from an industrial perspective, to allow the integration of such a 5G system into an existing Ethernet architecture, because most of the machine steering solutions are today cabled in using Ethernet. And the solution that is now included in release 16 is going to be finalized, as I said, by September this year, is to have support for 5G within that TSN time-sensitive network architecture. And that is done or realized essentially by creating or establishing the 5G system as essentially a TSN bridge. So you can see you've got certain translator functions at each side of the 5G system. So on one side, from the user plane function, so out of the core network into the TSN network. On the other side, it is the translator function from an end user device towards the TSN system. And there's also a specific TSN anchor function in the control plane of the 5G system that talks to the TSN system. So by this, you essentially allow to cut a cable within your existing implementation, put in the 5G system, and then from the existing environment, it would be perceived as a traditional TSN bridge only. Let's look to this a little bit more in detail. So how is this realized, or what are the key cornerstones to realize this? On one side, you have to be cautious about the time synchronization, because we want to support the specific time-sensitive networks used based on Ethernet. And there, those or the time synchronization is explained on the left-hand side here. So essentially, the 5G system calculates and adds the measured residence time, so the time that is used within the 5G or that is occupied within the 5G system, between these translator functions on either side, on the UE side and UPF side. And these are taken into account for the correction fields of the synchronization packets of the TSN working domain. You have that described in much more detail in specification 23401. And also, on top of that, the node Bs may signal certain time reference information to the end user device in the 5G system itself. They can do this by broadcast RFC signaling or UDICAS are signaling, and that is down to a granularity of 10 nanoseconds, so quite precise. And the other main part of that enhancement in RE16 is that we provide information out of the TSN working domain towards the 5G system, and that information is related to the TSN traffic we can expect. So the periodicity of that traffic and also the different patterns that are used, if that is known to the 5G system and that it's questioned and then transferred further on into the control plane by this TSN anchor function in the core network, then these quality of service flows I explained earlier, they can be influenced to really allocate the right characteristics for the data radio bearers on the interface later on. So with knowing the TSN characteristics of the traffic, we can optimal schedule the traffic in the 5G system. So these are the two main components that are added in Release 16, and that's why the people wait for Release 16 implementations to become commercially available to really have big implementations into their target scenarios, let's say. Good. So I'm moving now on for my second major part of this presentation. So as mentioned, ROHDE SCHWARZ obviously is a test and measurement device manufacturer, but we also produce on products, of course, that we sell, and we have our own factories in Germany, in Memmingen and Teisnach, as well as close to the German border in Wimberg. So obviously we are also interested to use the 5G technology for our own production services. In these environments, we are looking for industrial grade performance. The reliability and security is very important, as I said. We also think that deploying 5G in a private spectrum would offer high efficiency and flexibility. And we have also the requirement that an existing network is already existing. Our factories are existing for quite a while, and obviously we would need to integrate 5G wireless services into that environment. There's a regulatory framework to be watched and to be monitored and fulfilled that I will discuss a little bit more in the upcoming slides as well. So we as ROHDE SCHWARZ are quite interested to use 5G for our own purposes. If you want to do this, you've got different possibilities how to deploy the 5G network actually. That is described nicely in a 5G ACA white paper. It's called 5G Non-Public Networks for Industrial Scenarios. I quickly dig into the four main scenarios that are described in this white paper. On the one side, you can see that as in one extreme, if you like. The scenario described is so-called the isolated scenario. That means that as an operator of your own factory hall, of your own area, you would deploy the complete cellular network, including the core network, including the RAN access network, access points, as well as, of course, the user devices on your own. So you will not rely on a public network in that case. That is then a totally independent network from what the outside world is doing. On the other side, you can think of working together with a public operator that then would provide all these services to you, most likely is going to offer that in combination with the so-called network slicing technology. That means via software options and software implementation, a dedicated slice of a public network is dedicated to your premises, to your services, and beside of the application data and the application itself, everything else is actually provided by the public operator. So also the coverage is then coming from the public operator, and you just take care of the application. So these are the two extremes, if you like, you can think of: working on your own and then working with a public operator in combination. In between, you can think of some shared scenarios. One shared scenario is then only sharing the radio access network or the access point. That means that you keep all the core network functionality and also the user credentials within your environment, but you share the radio access network with the public operator. If you also let the public operator deal with the core network functions and also with the management of the subscribers, you've got a shared run and control scenario. I mentioned earlier that in the isolated non-public scenario, we believe that, at least from a ROHDE SCHWARZ perspective, we can use that for highest reliability and also operation flexibility reasons. Now, if you start deploying such a network, what are the testing requirements, or what should you do actually to make that a successful project at your end? Well, first of all, you should look into your area and make sure that the spectrum you like to operate is not interfered by any other electronic devices. So I said earlier that in Germany we have got this specific situation that we are allowed to use a spectrum portion between 3.7 and 3.8 gigahertz dedicated for 5G or LTE operation, but only allowed for your own premise or your own ground. So you can apply for that spectrum and then it's yours. So obviously you want to make sure that there is no interference in that spectrum before you do your rollout. That is the preparation phase. The next step would be, after installation of the 5G NR or LTE network, that you do a site acceptance testing. So you verify that everything works according to what has been specified before. And that is extended then maybe for specific coverage and performance limits to check. You would of course try to understand if the coverage is in any areas that you intended to do, be it available. And important to note here is that this is maybe a task you don't do once after setup of the network, but you may check this on regular terms because you want to make sure your coverage and your performance is of course continuously achieved. And there's also the subject of service level agreement verification. So if you have ordered that system from a third party, then potentially you've got agreed on certain criteria to be fulfilled firsthand, and these need to be checked. And again, that is something maybe you check on a continuous basis later on. Finally, regulatory obligations. So I mentioned situation in Germany where you are allowed to operate that network on your own premises. Certainly it may be the case that your neighbor or the neighboring area, another campus networks, is operated by a different party. And in that case, both networks are running the same frequency. So there are regulatory obligations that you are not allowed to exceed certain power levels at the boundary of your premises, just to avoid any interference to your neighbor. Of course, vice versa, this is the case. And in that case, of course, you need to check these power limits at these positions according to the rules. What is the test solution that you can use for this? You've got two different main areas here that I mentioned. I mentioned spectrum clearing and also site acceptance in terms of coverage verification For this you can use spectrum handheld analyzers. You can also use scanners in combination with the ROHDE drive test software that would allow you to assess the complete picture. Also, in case if you've got 5G NR beamforming applied, the scanner solution will allow you to measure the beam power of each individual beam. So this is a very suitable tool. It can also be operated with a battery pack, so you can carry this around without any power supply. So this is most suited in these scenarios. If you want additionally to check the quality in terms of the connection quality, so in terms of throughput or even latency, then the QualiProc solution is most suited. So this is a smartphone-based hardware solution where the measurement application is put on that hardware, and you can see not only coverage, not only signal-to-noise ratios, but also the connection parameters, including the complete messaging. So you will be able to see the throughput figures as well as the messaging flow going forth and back. Certainly these data, all the data can be analyzed also in certain data analytics tools on ROHDE SCHWARZ sites. This is called Smart Analytics, and you will be able to centrally evaluate the results from these measurement tools. Just to give you an impression, here's a small video how such measurement equipment can be mounted on a drone, and then you can fly around with these drones, as I mentioned, maybe at the boundary of your premises to check the regulatory applications I mentioned earlier. So also here it is shown how the data can be centralized or can be stored centralized and worked with afterwards. In 5G NR for industrial applications, we have this specific item of latency, and I shortly like to touch on this as well. So there is a commercial solution based on this QualiProc that I mentioned already, and the round-trip measurement that is explained on this slide is using IETF protocol, the T1 protocol, where the server is simply reflecting packets in the most fast way, so that you at the user device side can measure the round-trip delay. Important to note is that you can vary the packet rate and packet size. So according to different data rates, you can really assess your latency for the different system loads, if you like. On the left-hand side, you see an LD measurement that's been done. In the middle of that screenshot, you can see the number of packets that got lost, 6 out of 3,625 in that case. You see a median latency, round-trip latency of close to 45 milliseconds. And also you have a packet delay variation measurement. So things like a jitter, if you like, which was close to 10 milliseconds in this case. So this is a very nice solution to assess the latency in your system. It can be used obviously also for industrial applications if this T1 server is installed at your edge cloud server, as an example. Then in industrial application, we also are often asked, is round trip enough? What do we need to support one-way latency measurements? That means in a machine control scenario where the actor is sending a command and the machine has to react, potentially you are interested into the one-way latency. Also here we have a prototype solution established. It's again a piece of software put on a smartphone, and we have GPS on both sides. The other side would be a server. For a prototype solution we used a server in Munich, and you can see that with a little bit of synchronization procedure and then sending timestamp within the packets, you are able to measure the one-way latency. Again, these were measurements now on an LTE network with a medium latency in one direction only of 15 milliseconds. So this might be quite interesting in future to understand whether or not the delay in different directions would differ. And that's already all that I wanted to explain to you in this very short session. Let me quickly summarize. We see a real high interest from different and multiple work verticals for 5G deployments. However, automotive and industrial applications like Industry 4.0 scenarios are really the main drivers in this respect. We have test solutions for the required tasks that are needed when you have deployed such private campus networks. We like to emphasize this interactivity test, which is quite nice because it allows you to do round-trip latency measurements, at the same time to assess the packet delay variation, and at the same time to assess the packet error rate, so the data throughput, if you like, and that is all possible in a single test. We believe really that in future for these scenarios it's not sufficient to test only once. We believe that also the monitoring of different parameters needs to be done on a regular basis. And if you do so, obviously you would rely on machine learning algorithms to detect certain anomalies in your operational environment. That is something also ROHDE SCHWARZ is working on at the moment. So all in all, we like to emphasize that we provide the test solutions to maximize the 5G network quality and performance, specifically also for industrial applications. So this was a very short extras from my home office, potentially into your home office. I like to thank you for your attention and hope to see you soon again on this channel. Thank you so much.